Okay, so have you ever stopped to wonder if a computer program could actually understand its own rules? I mean, not just follow them, but really analyze, represent, and maybe even change them? Well, today we're diving into a super fascinating corner of computer science that does just that. We're going to explore a really powerful concept called rewriting logic.
So here's the plan. We'll start with the basics. What is this thing? Then we'll look at why it's considered a universal framework. After that, we'll get into the really mind-bending idea of reflection, see how it all works in a language called Maude, and then, tie it all together to see why this is such a game changer.
All right, first things first. What exactly is rewriting logic? I know, it sounds pretty complex, but the core idea is actually incredibly elegant. So let's break it down.
To really get our heads around this, let's start with a huge question. Think about it. We live in a world with tons of different programming languages, computational models, and logical systems. So how could you possibly create one single system that has the power to understand and represent all the others? That's the exact challenge that rewriting logic was built to solve.
Right. So here's the crucial point. Rewriting logic isn't just another programming language. It's more like a foundational framework. You can think of it as a set of meta-rules, rules about rules, that you can use to describe how any computational system works, from its basic structure all the way to how it runs. It's designed to be this common ground, a kind of universal stage for all of computation.
And that brings us to its first superpower, its incredible universality. If all the different logical systems out there are like different languages, then rewriting logic is kind of like the Rosetta Stone. It gives us a way to translate and understand all of them within one single unified structure. Now, what's really interesting here is how it compares to things you might already know. A lot of us have heard of specialized systems like Prolog, right? Which is awesome for logic programming, but that's its specialty. Rewriting logic is a whole different beast. It's so flexible that it can represent a huge range of models, things like Petri nets for modeling workflows, or process calculi, which describe how different computer processes talk to each other. It's this sheer breadth that makes it so uniquely powerful.
Okay, now let's see how this builds into something even more profound. Let's talk about the power of reflection. This is where things get really wild. It's where a system gets to look at itself in the mirror. This is one of the most abstract, but also one of the most impactful features of this entire concept.
So, the formal term for this is a C-reflective logic. Now, I know that sounds technical, but it stands for a simple yet totally stunning idea. It just means that the logic's own meta-theory, the very rules that dictate how proofs and deductions work, can be represented and reasoned about inside the logic itself. In other words, it can literally talk about its own thought process.
So how in the world does that work? Well, it's basically a three-step dance. First, you take a problem and its rules, and you just represent them as plain old data inside the system. Step 2, a special universal theory acts like a master engine. It takes that data and runs the proof. And finally, this is the magic part, the result it spits out is guaranteed to be the exact same as if you had run the original proof directly. It's like it creates this perfect, trustworthy simulation of its own logic that it can then analyze.
Now I get it, this might all sound super theoretical. But what happens when you take these incredible ideas and build a high-performance system with them? Well, that's where we meet Maude.
Maude is where the rubber meets the road. It's the concrete implementation of rewriting logic. It's a real-world programming language that takes all that theoretical elegance and gives it speed, power, and practicality. Maude is what makes reflection not just a cool idea, but a powerful tool for solving really complex problems.
And because of reflection, Maude can do some truly mind-boggling things. You can use it to define and execute entirely different programming languages. Within it, you can build these heavy-duty theorem-proving tools to formally verify that other systems are correct. You can even define internal strategies to guide its own logical process, making it smarter and more efficient. Seriously, from mapping complex behaviors to verifying the integrity of database schemas, reflection turns Maude into this Swiss Army knife for formal reasoning.
So, let's zoom out for a second. We've talked about universality, we've talked about reflection, but what's the big picture? Why should we really care about this pretty abstract-sounding logic? It really boils down to this. Its universality gives us one single, unified framework to model and understand all kinds of different systems. It creates a common language for computation. And then, its reflection gives us the power to build tools on top of that framework, tools that can analyze, verify, and guarantee the correctness of those systems in a way that just wasn't possible before.
And that leaves us with a pretty fascinating thought to end on. We've just looked at a logic that can represent its own rules and reason about its own processes. So if a formal system can achieve this level of self-understanding, what does that mean for the future of computation, for verification, and maybe even for the path toward creating more self-aware systems? Now that's something to think about.